Okay, this is part 2 of the video, improper integrals. We're going to talk about functions with discontinuities. So we talked about what if we don't have a finite interval, we dealt with that, and now we're going to ask about what's going to happen if my function has an infinite discontinuity on the interval that we're integrating. So we have our rules here that if I have a discontinuity at x equals b and I'm integrating from a to b, then I'm going to approach that bound that has the discontinuity. If I have a discontinuity at a, and a is my lower bound, I'm going to approach that bound. The only thing I didn't specify here is that we have a directional limit here. If I'm integrating from a to b, and I'm going to let my t-values approach b. Okay, if I'm approaching b, I would be approaching b from the left. Okay, so this limit should be the limit as t approaches b from the left. Okay, and if I'm approaching a for the second limit, for this one, if I'm approaching a, then I'd be approaching a from the right. So this actual limit should be the limit as t approaches a from the right. Okay, so that said, I'm going to deal with those discontinuities that way. And then if I have discontinuities at someplace in between, okay, so if I have a discontinuity someplace in between, I'm going to have to break up the integrals and look at each one individually and deal with those bounds, much like I did with that problem where I had both infinity and negative infinity for bounds. Okay, so let's look at some examples. All right, let's look at the integral from 2 to 5 of 1 over square root of x minus 2 dx. Now, these integrals are a little misleading because they look totally fine. They don't look harmful in any way. There's no infinity for bound, but if you look that I have this rational function, and if you think about the domain of that rational function, the function's undefined at x equals 2, yet I'm asking you to integrate starting at x equals 2. Okay, so that is my bound, that's my problem. Okay, so try to set up a limit so that I'm approaching that bound instead of plugging in that bound. Pause and come back to me. So I'll have the limit as t approaches 2 from the right, and I know that notation is a little off, but that's the best I can do with my program, of the integral from t to 5 of 1 over square root of x minus 2 dx. Okay, now I'm going to go ahead and integrate this. Now, that is a composite function, so it's going to require a u sub. Now, you got to be careful with your u subs because we always talked about changing our bounds and not changing our bounds and u's bounds and x's bounds. Not only do I have x's bounds now, I also have a limit that belongs to x. So when you're doing your u substitution, please do it totally on the side and then come back to the limit and the bounds. So let's see what that would look like. So we'd let u equal x minus 2, and then d would be dx, and when I make the substitution, it would look like this. I'd have the integral of u to the negative 1/2 du, because that's my 1 over square root of u to the negative 1/2, and then when I integrate, I will get 2 u to the 1/2, right? Increase the x by 1 divided by du, which is 2 times square root over u. Okay, so I'm doing that exclusively on the side, and then I'm going to come back to my limit, and I will have the limit as t approaches 2 from the right of square root of x minus 2 from t to 5, and if I do upper minus lower, it's going to look like this. The limit as t approaches 2 from the right of square root of 5 minus 2 or square root of 3 minus square root of t minus 2. Okay, once again I have an algebraic expression, I can evaluate my limit, which means try plugging in, and it really doesn't matter that I'm approaching 2 from the right on this particular problem, but it might on others. If I plug in 2 for t, this part is going to approach 0, which means I have square root of 3 minus 0, which means my answer is square root of 3. Okay, so this integral converges to square root of 3. Let's do another problem. Let's look at the integral from 0 to 3 of 1 over x minus 1 dx. Okay, now again, this doesn't scream improper integral to me, but if you think about the domain of the function 1 over x minus 1, I have an infinite discontinuity at x equals 1. Okay, that means that I'm going to have to rewrite this integral as the sum of two integrals, breaking it up at x equals 1. And that would look like, well, hopefully pause the video, try breaking up the integral, and then come back to me. Okay, so I should have the integral from 0 to 1 of 1 over x minus 1 dx plus the integral from 1 to 3 of 1 over x minus 1 dx. Now, just like when we were doing our improper integrals on an infinite interval, I told you if you were looking at two integrals, just work with one, and if either integral comes up as divergent, then the entire problem is divergent. So when you're working with two integrals, work one at a time. All right, if I have to choose between the integral from 0 to 1 or the integral from 1 to 3, I'd rather work with the integral from 0 to 1 because I love having 0 as a bound. So I'm going to work that integral first, and if I have if I come up with the convergence, then I'll do the second integral. If I come up with divergence, then I'll stop, and I am done with my problem. So go ahead and work that integral for me, pause the video, and come back to me when you're done. Okay, so I'm looking at the integral from 0 to 1 of 1 over x minus 1 dx. Okay, I'm going to have the limit as t approaches 1 from the left this time, and again, that notation's a little funny, but it's the one from the left of the integral from 0 to t of 1 over x minus 1 dx. Now, this integral technically needs a u substitution, but I'm going to assume that you guys can handle that on your own. Your u would be the denominator, x minus 1. Your du would be a plain old dx. I'd have the integral of 1 over u du, which would give me natural log absolute value of u, and that would bring me to natural log of absolute value of x minus 1. So I'm going to have the limit as t approaches 1 from the left of natural log of absolute value of x minus 1 from 0 to t. When I do upper bound minus lower bound, I'm going to have the limit as t approaches 1 from the left, for some reason that disappeared on me, of the natural log absolute value of t minus 1 minus the natural log of absolute value of 0 minus 1. The natural log absolute value of 0 minus 1 is natural log of 1, and natural log of 1 is 0, so this part is just 0. And now if I'm approaching 1 from the left, I'm going to have natural log of values approaching 0 here, and if you think about the natural log graph looks like this, and if you're approaching values of 0, your values are approaching negative infinity. Okay, and if I approach negative infinity, that means that my integral is divergent. Okay, and if I'm getting divergence on one of these two integrals, I am done. I don't need to consider the other one. My integral is divergent. Okay, so my answer is divergence. Okay, so again, please don't work the integral simultaneously, because if you get divergence, you are done. All right, let's do one last example. I've got the integral from 0 to 1 of natural log x dx, okay? And I just graphed the natural log function for you. It is undefined at x equals 0. I've got a vertical asymptote there, so that's going to be my problem bound. So please pause, work the problem, and come back to me. Okay, so I should have the limit as t approaches 0 from the right of the integral from t to 1 of natural log x dx. If you remember, we just did this integral when I was doing iteration by parts, so I'm going to just cut to the chase. And I'll have the limit as t approaches 0 from the right of x ln x minus x from t to 1. Okay, if I do upper minus lower, I'll have the limit as t approaches 0 from the right of natural log of 1 minus t natural log t plus t. Okay, now natural log of 1 is 0. And if I let t approach 0, t will approach 0. So this is what I need to focus on. Okay, and if I let t go towards 0 from the right, I'm going to have a 0 times negative infinity, which if you guys remember, we called that an indeterminate form with L'Hopital's. So I'm going to have to L'Hopital that limit. I will consider that separately. If that didn't occur to you, please again pause, try to evaluate that limit using L'Hopital's, and come back to me. So I'm considering the limit as t approaches 0 from the right of t natural log of t, which I'm going to have to turn into a quotient in order to L'Hopital it, which would look like that. Okay, I'll have the limit as t approaches 0 from the right, I don't know where my right went to, of natural log of t over 1 over t. Take derivative top, derivative bottom, and I'll have the limit as t approaches 0 from the right of 1 over t over negative 1 over t squared, which if I simplify that algebraically, I get the limit as t approaches 0 from the right of negative t, which is 0. Okay, that means that this part is also approaching 0, so the value of this is negative 1. Okay, so it converges to negative 1. All right, that is it for our improper integrals.